Hello everybody. So today I'm going to talk through the experiment where we synthesize a dipeptide. So some of the basic stuff we'll meet today is coupling reactions, syringe use in organic chemistry, and acid-base reaction workups. So learning outcomes. So by the end of today's particular class, you should be able to use a syringe for synthetic organic chemistry, understand the role of coupling reagents, and how to do an acid-base workup. Okay, so when we form dipeptides, we form a molecule with a bond between two amino acids, and these two amino acids are joined together via a peptide bond. So here we have an example of where we are combining phenylalanine and proline to make a dipeptide. Okay, and the structure shown has a phenylalanine proline dipeptide. Now, the two amino acids can combine in four different ways. Proline, phenylalanine, proline-phenylalanine, and proline-proline. So not a very efficient synthetic method if you were just looking to form one of these dipeptides. So to avoid the formation of a mixture of products like this, we use protecting groups, and these protecting groups need to be installed in the reacting amino acid starting materials. So protecting groups, when reactions are not chemoselective, more than one functional group can react with another, protection of functional groups is used. This involves the chemical modification of a functional group to avoid mixtures of products in a subsequent chemical reaction. And then deprotection, removal of the protecting group, takes place after peptide bond formation has occurred, and this will give the unprotected peptide. So we will do protecting group chemistry, we'll do our coupling reaction to form our dipeptide, and then we will remove the protecting groups. That's the theoretical process. So in this case, if we wanted to couple phenylalanine to proline and just make this dipeptide and not the other three as well, we would need to do some protecting group chemistry to prevent that happening. So in that scenario, we would put a protecting group, as you see here, on the C terminus of phenylalanine, stopping reactivity at the carboxylic acid. And we would put a different protecting group on the N terminus of the proline, again, preventing reactivity at the N terminus. So now what you see, we have the carboxylic acid end free on the proline and the amino end free on the phenylalanine. And that is the only bonding or dipeptide bond formation that can take place. So we only get a single dipeptide, the proline-phenylalanine dipeptide that we desire. Okay, so in terms of protecting groups, the protecting groups we will use for the experiment today is the acetyl protecting group. So we will have N-acetylated proline. So that will protect the N terminus of proline. And we will use the methyl ester of phenylalanine. So you can see we have the methyl ester here instead of the carboxylic acid, and that will act as a protecting group for the C terminus of phenylalanine. So you will make or will have made the acetylated proline already, or you will make it in a subsequent week, where we add the acetyl group onto the N or nitrogen of proline. And then today what we will be doing, we will be coupling the N-protected proline, so the acetylated proline, and the methyl ester of phenylalanine to form our dipeptide you see here. So you can see what we are forming a bond between the carbonyl of the carboxylic acid of proline and the nitrogen of the amino group of phenylalanine. We form our new peptide bond here and form our dipeptide. And we will have our protected group still in place. Now we won't deprotect them today. We will be just going as far as making the dipeptide here with the protected group still in place. So we will use a base called N-methylmorpholine, and it's going to act as a base for us removing the proton and free up the amine on the phenylalanine for nucleophilic attack. So here we have our methyl ester of phenylalanine, and you can see the nitrogen is protonated, and we'll use the N-methylmorpholine to deprotonate the nitrogen, giving us our reactive nucleophilic site here. And here's the structure of N-methylmorpholine. Isobutyl chloroformate is another reagent we will use, and this is the coupling reagent, and it's used to form an activated intermediate with the N-acetyl L-proline. So here we have our N-acetyl proline, and we're going to use the isobutyl chloroformate you see here. We're going to react those two together to form this intermediate. And what it has done, as you can see here, it has put this excellent leaving group on to the C double bond O here. So instead of an OH, we now have this excellent leaving group. This will be nice and reactive to react with our phenylalanine. And here is the electrophilic site, the carbonyl-carbon for a dipeptide coupling reaction. Now, just so you note, when it does react with the phenylalanine, this leaving group will leave and it will degrade into carbon dioxide and butanol. So, the coupling reaction itself. So, as I said already, we have the acetylated proline reacted with the isobutyl chloroformate to form our reactive intermediate with the excellent leaving group. Then we add in our methyl ester of phenylalanine and our N-methyl morpholine, and they will react together. So we have our electrophilic site on the carbonyl carbon of the activated proline, and we have a nucleophilic site on nitrogen on our phenylalanine, and they will react to form our dipeptide, and we get our new peptide bond formed between the two amino acids. So the overall coupling reaction is between the acetylated proline, our methyl ester phenylalanine, with N-methyl morpholine as our base, and isobutyl chloroformate as a coupling reagent to give us our protected dipeptide. And if you were looking to access the final dipeptide, you would then have to go through a deprotection step. So in terms of today's experiment, do look at the health and safety and hazard statements in your manual, particularly mindful of chloroform, N-methyl morpholine, and isobutyl chloroformate. So today's procedure will involve you dissolving 0.75 grams of the N-acetyl L-proline in 20 ml of chloroform using a 100 ml round bottom flask. You're going to cool that resulting solution in an ice bath. You're going to add a stirring bead, 0.65 milliliters of your base, the N-methyl morpholine, and 0.85 milliliters of isobutyl chloroformate, your coupling reagent. And you can add that coupling reagent using a syringe, like you see here. Okay, so the isobutyl chloroformate comes in a bottle with a septum on the top. You need to syringe out the septum, syringe out the isobutyl chloroformate using the syringe from the bottle through the septum. Isobutyl chloroformate comes in a septum bottle in order to prevent it reacting with moisture in the air. It can be quite reactive in that sense and react with the moisture in the air. So it's under an inert atmosphere in the bottle, under nitrogen atmosphere. What you see here is with this syringe poking in, it's got a balloon here containing a balloon of nitrogen gas, and that balloon of nitrogen gas gets pulled in as you pull out the isobutyl chloroformate, keeping the atmosphere inside the bottle inert in the nitrogen atmosphere. Do look at the video online of this lab and you'll see that happening. So at that point then you stir for 10 minutes on ice and add 1.3 grams of L-phenylalanine methyl ester hydrochloride. And then you add a further 0.7 ml of N-methyl morpholine and stir the resulting mixture for 10 minutes at 0 degrees centigrade. You now allow the reaction to warm up for 30 minutes to room temperature and pour into a separating funnel for workup. So at this stage we should have formed our dipeptide, and now we want to work it up and try and purify it. And this is where we do an acid-base reaction workup. So you have your reaction solution. You're going to wash the reaction solution, the organic phase, with two portions. Two 20 milliliter portions of 2 molar HCl. You're going to separate the aqueous and organic phases into two different conical flasks. Then you're going to take the organic phase and wash that with two 20 milliliter portions of 1% sodium bicarbonate. Carefully vent and release the large amount of CO2 that's going to be produced. So just be careful at that point in terms of releasing and venting the CO2 that's produced. Do talk to your demonstrator about this before you do this part of the experiment. Separate the aqueous and organic phases again into two different conical flasks. Dry the organic layer with anhydrous sodium sulfate and filter into a 100 milliliter pre-weighed round bottom flask. So weigh your round bottom flask empty before you filter your organic layer into that round bottom flask. So just to talk a little bit more about acid-base reaction workup procedures. So you are familiar with having an aqueous layer and an organic layer. When you separate into immiscible liquids, the lighter liquid will be the top layer and the denser liquid will be the bottom layer. So in your experiment today, the water will be the lighter liquid, it'll be the top layer, and chloroform is the denser liquid, it'll be the organic layer and the bottom layer. The denser density of chloroform is 1.49 grams per milliliter. So it's it's a higher density than water. Organic compounds are mostly insoluble in water. In this experiment, both the reactants, so the starting acetylated proline and the methyl ester of the phenylalanine, as well as the product, are soluble in the organic layer. So they're all soluble in the organic layer. However, the two amino acid starting materials can be made water soluble by ionizing them in acid-base reactions. So if we can ionize the two starting materials and make them water soluble, they can move into the water layer, leaving just the product behind in the organic layer, and hence we will have purified the product. So the resulting two ionic compounds are soluble in the aqueous water layer, as I said, and that will allow us to separate them from the product in the organic layer. So in terms of the methyl ester of phenylalanine, if we react that with HCl, so we do an acid wash, it'll protonate the amine group to give an ammonium ion, and you can see we now have an ionic species that will be water soluble. In terms of the acetylated proline, if we react that with base, we'll be able to do a deprotonation to form the carboxylate, and again you see we have formed a salt, and that will be water soluble, and we'll be able to move that into the water layer. So for the first wash in this experiment, what you'll be doing will be a wash with 2 molar HCl, and that protonates the amine of the phenylalanine amino acid, forming the ionic ammonium salt, and this makes the amine water soluble and removes it from the organic layer. It moves into the water layer. The second wash is with saturated sodium bicarbonate, and that deprotonates the carboxylic acid group of the amino acid to form the carboxylate. Okay, and this makes that amino acid water soluble and removes it from the organic layer and into the water layer. So after these two washes, the acid wash followed by the base wash, the organic layer should only contain the product dipeptide. So then we move to the final steps, and this leaves the product as the only remaining component that is soluble in the organic layer. Now one can move on to isolating and purifying the product from the organic layer. So remove the solvent using a rotovap, and that leaves an oily residue behind. Record the weight of the crude oily product at this point. Cool to room temperature and add a minimum amount of cold ether to precipitate the product as a solid. Then you're going to have to collect that product by vacuum filtration, weigh and determine the melting point. I just want to comment on anhydrous conditions. So you did note earlier on that we had a balloon and a syringe to access the isobutylchloroformate, and that's because the isobutylchloroformate can react with moisture in the air. So anhydrous conditions can be important. They can be important to avoid undesired side reactions and prevent decomposition of moisture-sensitive reagents. So water in the air or in your solvent can act as a nucleophile, can act as an acid, or can act as a base, and it can conduct side reactions, unwanted side reactions, and give you complex products that you're not looking for. So in today's experiment, water can react with the coupling reagent isobutylchloroformate. So we wanted to keep moisture from the air away from that. So to do that, you would often use oven-dry glassware. You may use drying reagents like calcium chloride. And to avoid contact with moisture in the air, you will use an inert atmosphere. So you'll use nitrogen gas or argon gas that is unreactive, and that can be supplied through a balloon. And that's what you'll see today in the experiment, where you'll have a balloon of nitrogen gas placed through the septum via a needle into your bottle of isobutylchloroformate, and then you use a syringe to syringe out the isobutylchloroformate and therefore avoid its exposure to moisture in the air. Other methods for avoiding contact with moisture in the air and using an inner atmosphere include use of glove boxes and Schlenk lines, but we won't be using those today, but you can look those up to see and learn a bit more about them. Also, of course, to avoid moisture in your reaction, you will want to use anhydrous solvents. To use anhydrous solvents, you first need to dry the solvent, and there's different drying reagents we can use to do that. Reagents like calcium hydride, sodium and benzophenone, or molecular sieves can be quite effective at drying out your solvent, removing any moisture from the solvent, and therefore removing any moisture that may be able to cause any undesired side reactions. Okay, so just to bring us back to what we're working at today, we're going to work with our acetylated proline. We're going to work with our methyl ester of phenylalanine. We're going to do our coupling reaction between those two using our base N-methyl morpholine and our isobutyl chloroformate, and that's going to form our dipeptide here, our protected dipeptide. We won't be deprotecting that today, but we'll be stopping